Hello, my name is Trinity Griffus. I am the ChiliHouse undergraduate lead for this year's project. I am a sophomore majoring in biology, and this is my first year with NASA Mines. ChiliHouse is made up of undergraduates in biology, biochemistry, and computer science, as well as supportive faculty and graduate. Last year, our team's goal was to use innovative techniques to grow crops autonomously for use on the surface of the Moon and Mars to aid in the Artemis mission. We used autonomous robots to monitor and water crops grown in 3D structures made from simulated in situ resources. We grew New Mexico chili peppers since they were the first fruits for astronauts to eat aboard the International Space Station. For this year's project, we pivoted our focus to food production technologies compatible with the APH and veggie systems aboard the ISS. Our goal was to develop an autonomous system to monitor and care for the plants in place of the astronauts. These efforts are crucial for freeing up the astronauts' time, increasing scientific research capacity, and ensuring sustainability in future space exploration endeavors. We had 4 aspects to our project: plant growth, APH analog, robo-gardener, and RealSense camera. For our plant choices, we ultimately decided on using Arabidopsis thaliana due to their rapid growth and life cycles, which allowed us to have multiple generations. Unfortunately, we didn't use the Capsicum annuum, commonly known as chili peppers, or Fragaria ex ananassa, commonly known as strawberries. These plants were in our original plan, however, the chilies didn't have a rapid growth rate, and the strawberries needed to be taken from the runners from pre-existing strawberry plants. We needed a plant that was going to be able to sprout from seed and grow quickly within a compact space. We have 3 generations of Arabidopsis, one of which never germinated due to a light issue where the grow light never turned off and fried the seeds and any potential sprouts. This was a prime example of why the need for a rapid germination and growth rate is important for this project. For the APH analog, we used readily available tools and equipment located within our labs to replicate important aspects of the APH. For example, the tent, lights, and temperature and humidity sensor were all sourced from our labs. The basins and their lids were 3D printed in-house with PLA filament and then tested to ensure they didn't leak. The basins and lids were designed so that they could be reusable for continuous generations of plants, making gardening in space more sustainable. During the 2nd and 3rd growth cycles of Arabidopsis, we tested different lid types attached to basins. We were able to find which lid type proved to be most effective for water retention and plant growth for future use. For the robo-gardener, we needed a modern CNC machine that was capable of tool changes and had a well-defined language called G-code to command and pull data from a tool that aligns with our needs. For the base of our machine, we acquired a discarded 3D printer that had several missing or damaged parts. After designing a custom generic tool holder to replace the missing head, we had our first iteration. Following the first iteration, we were able to reconstitute it into a working CNC. For monitoring the plant's growth and health, we decided to use RealSense LiDAR cameras that had 3 different image types: RGB, infrared, and point cloud, otherwise known as depth perception. With this multifaceted camera, we were able to thoroughly monitor the plant's health and growth without constant intervention. We used this camera for monitoring the entire module. We plan on also using a smaller camera called the RealSense Depth camera, which is the size of a golf ball. Its size would be suitable to attach to the robo-gardener's head to get closer, more in-depth images of the plants. In the future, we will use a human gardener's in-person inspection assessment of plant health and maintenance procedures compared to an assessment made through the analysis of camera data and maintenance done by the robo-gardener. This comparison will help determine the efficiency of the robo-gardener. We plan to extend our outreach to a wider audience of undergraduates to take part in this amazing opportunity. Our goal is to utilize presentation opportunities such as conferences, info booths, colloquiums, and various classes to reach as many different majors across our campus as possible. This will ensure that we have a diverse team. We also now offer a college credit option to encourage the attendance and participation of students. Our final improvement to the overall workflow of our project will be making the timeline year-round. We will start onboarding students during the summer and early fall time to get them familiar with past projects and begin brainstorming for the upcoming project. That way, during the spring, we will have a fully prepared team ready to begin the project. Here is a statement from one of our first-year participants.
Tatyana Falkowsky, Biochemistry. NASA Minds has been an extremely positive experience. The entire team was welcoming, knowledgeable, and extremely open to teaching newcomers. At the beginning of the semester, I knew nothing about astrobiology, and I honestly didn't care to find out more. But now, I'm excited for next year, and I want to keep developing the Robo Gardener and see what we can get it to. This is my first exposure to research at a university, and I'm so happy I participated. I've learned so much in such a short amount of time, and I feel much more prepared to just continue doing research in the future, especially with plants.
As for myself, being the undergraduate lead has taught me a lot about communication, project management, writing technical documents, and so much more. I have gained a better understanding of what my strengths and weaknesses are and strive to refine my skills throughout the duration of this project. We would like to extend a huge thank you to the Moses Biological Computation Lab at the University of New Mexico for the use of software, meeting spaces, and equipment. Also to the Hansen Lab at the University of New Mexico for providing space and equipment for plant cultivation, analysis tools, and ongoing guidance. Thank you to Jacob Valencia Torres, otherwise known as Jacob Pepperseed, for his expertise, resources, and guidance. And finally, on behalf of the ChiliHouse team, thank you to everyone for watching our video presentation.